Morning, everybody. Cormac already talked a little bit about our database and how you can search for properties. Just to recap, you can easily go to our website and use the search function to specify your elements or your element groups that you want to look for, filter whatever properties you like, and determine or specify the number of species. And here's an example. If you just want to get all binaries with number of species equals 2, with the certain band gap that you can filter and specify, you get essentially what you want. And that's fine for a casual search. That's fine for just doing a quick search or occasionally looking for a specific entry. But that doesn't help us very much when we want to, for example, post-process a set of data, or if we want to use it programmatically in a Python script, for example, or for any other script that we might need, or to feed this data into, for example, a machine learning model. So we decided to expose our database and have others access it. Our database is essentially built in different layers. We have the very top layer here, which is our website, and we have different project layers. We have a project that is specifically dedicated to ICSD, and then lib1, 2, 3, etc. Lib1 being elements, lib2 being binaries, lib3 being ternaries, and so on. We have lib4, we have lib6, and all that. And the next layer is the set layer, which is essentially the composition. Here we can see copper niobium alloys, copper vanadium alloys for lib2. Lib3 also has these ternary alloys, copper, niobium, vanadium, and each of them has different structures, different prototypes. David will talk more about this in a later session, but we have different sets, different calculations, and each of these calculations has materials data. And this is how such a data page looks like. We see iridium-3, titanium-1, it's an ICSD structure, and you have these all these properties like the density, for example, that you can access using these data pages. How do we get to these data pages? How do we get all that data? There's essentially two ways to do it. One is the so-called REST API, and one is Aflux. They have two different approaches. They mimic two different things, and I will introduce the REST API a little bit just to show that it's there and how you can use it, but I would like to focus the exercises on Aflux. The REST API is essentially mimicking our database structure. It is a URL, an AFLOW URL, that consists of the following elements. We have a server, we have the project layer, the set layer, and the entry layer, and a search keyboard, which is essentially mimicking the hierarchical structure that I've shown before. So here's an example. There's a ternary Heusler structure, copper 2, titanium, zinc. And this is the so-called prototype, which is a structure designation that David will talk about in detail later. And we can see the structure based on this link here. We have our server, which is the very top layer. Then we have the project layer, which is lib3_raw. And we have the set layer, and you see there's copper, titanium, and zinc. The _PV and the _SV, if anybody knows, people who know VASP knows what that means, but this is essentially the pseudo-potential. It means that the p electrons are valence electrons. Here's the prototype that we can see here, and this property here displays returns the enthalpy of formation. And that becomes a URL. Just be sure to replace the colon here with a slash, and you can actually put this into your browser. And yeah, you can essentially put this into your browser and get an answer. And you can also get the full list of structures using this particular link. There's a question, are there any other similar database of inorganics out there similar to AFLOW? There is the materials project. I think Nomad is another one, but the materials project I think is the biggest after AFLOW. And OQMD, thank you, Conrad. So this is the REST API. Are there any other questions? just quickly. No, cool. So this was an introduction, a quick introduction to the REST API. This is all fairly abstract, so let's actually look at quickly how this works. And for that, let's open the Colab notebook. Here. Don't forget to save a copy to your drive. And here you have the picture. Again, here you see the layer. You can compare kind of the how the REST API is connected to the layer. You have the server and the project layer with ICSD and everything. The set layer is your composition, and the entries are the Heusler structure here. You can see the nice one-to-one correspondence, and you can take this link, and actually add it to your browser, and you get an answer. In this case, the enthalpy of formation is negative 1.69. And incidentally, the data page I showed you earlier, if you just remove the keyword, you get to the entire set of properties that we have. For example,
Marco, can you make the font bigger, or?
I certainly can, yeah. Is that good?
Yep. Oh yeah, much better.
All right, yeah, I definitely can. Here you see the enthalpy of formation for each per atom of the cell. You can get space group information, for example, as another property. So you can access this into your browser. So, or you can access this using your browser. So that doesn't necessarily help us if we want to actually put this in a script. So you can, for example, in a non-Python script, use just curl to get the response here. It's the same response we got in our browser window. And if we want to look at the entries for that particular composition, we can just query that, and we get a comma separated list. That's one way to do it. The other way to do it is to use a Python script. And I've put it here. As I said, I don't want to talk too much about the REST API, just show you that it's there. But here's how you can actually use a Python script to get where you need to go. You essentially need to build the URL. I recommend using this structure here, where you have the project layer, the set layer, and the get the entries.
If you can make that bigger too, can you?
Oh yeah, sorry. Is that good?
Yep.
Okay. So essentially, you build your URL with your Python script, and then just use the URL open function in the URL lib extension to get your response. In this example, Python script just fetches the space groups of all these copper, titanium, zinc alloy systems. And what it does is it gets all the entries in that system, and then just uses essentially that link here to query the responses, except for that we use the space groups instead of the formation enthalpies. So let's just let it run, and we can see that it queries a bunch of responses. Here we have the prototype T0001.A2BC, and that is space group 225, so that's the rock salt structure. And 216, for example, is, I think, the zinc blend structure. So yeah, this is essentially how the REST API works. You can look through that script on your own time if you want to, but the REST API is, the REST API is one way to access our database. There's one very obvious disadvantage, though. You need to know how our database looks like. And as we saw earlier, we have this set layer copper PV and TISV. So you need to essentially also know how our what pseudopotentials we were using for our DFT calculations. That is all. That's all fine if you know what you're looking for, but it is, you kind of have to read our minds a little bit. So can we do better? The answer is yes. It's obviously a rhetorical question, and that is Aflux. Aflux is using a very, very different approach. Aflux is essentially trying to mimic how our search function works. So we've already played with the website. We already played with the search capability of our website. And we've also seen the data page. So can we combine the two into a programmatic way to get what we need using Python or using any kind of scripting language that we need? And the answer to that was Aflux. It is essentially programmatically exposing the same functionality as our web search using only very, very few operators. And I'm going to introduce the operators in a little bit and then show you an example. And then we will essentially just use a few exercises so you all become a little bit familiar about how Aflux works. Because it's a very, very powerful tool, but it takes a little bit of practice to get used to. The operators are actually very, very limited. We have a block operator, which essentially just encloses and delimits and delineates certain logical operators. We have an AND and an OR operator. We have a NOT operator. Anybody who's done coding should be familiar with these operators. We have the so-called loose operator, which is kind of a wildcard operator. I will show you in the next example how that works exactly. We have a string operator, so you can designate that something is a string using a single quote, not a double quote. And we have a mute operator. The mute operator suppresses output, so you can, for example, search for the number of species to be 2, for example, but you maybe not want to have that in your output because it's going to be 2 for everything anyway. So you can use it with that, using that. You can suppress it using that operator. Here's an example of how to use an Aflux query. We have a server, just like with the REST API, and then we have 2 different parts of it. The first one is a matchbook. The second one is a so-called directive. And I will explain now how these 2 work. The matchbook is essentially your search query just converted into an actual command. This example here, we have certain database properties. The species, for example, limits which species you want. And if we remember the operator, the comma is the AND operator and the colon is the OR operator, which means that we here limit our species to sodium or potassium and chlorine. So we're essentially looking for sodium chloride or potassium chloride in different structures. That is what this entire logic here means. And species is set to 2, so we don't get any sodium, potassium chloride solid solutions or any kind of sodium chloride mixed with other animal elements, for example, oxygen. We want to have it limited to only 2 species. EGAP is the band gap, and here we see what the loose operator does. It essentially says that we need a band gap between 1 EV and 5 EV. That's what we want. So we're looking for insulators here. An energy cell has no limits, but it's going to be output as well. So we're looking for sodium or potassium chloride with a band gap between 1 and 5 EV, and we're looking for the energy of the calculation per cell. You can get a full list of these directives using the schema keyword. So instead of having matchbook and directives, you just replace it with schema, and you get a big JSON that has all the properties that you can look for with descriptions and everything. The directives are the directives are essentially just formatting instructions. There are 3 that you can use. One of them is format. It can either be JSON or HTML. JSON is the default, and that is probably what you would want, so you can get all your results back as a JSON object. You can limit this by catalog if you really want to, for example, limit things by ICSD to ICSD entries. It is kind of tying back to our scheme that we had before, to our layers. So if you just want ICSD compounds, you can do that using the catalog directive. And paging is essentially telling you how many results you want back. Each page is 64 entries, and you can get all entries, but if you actually use that query in a browser and you have a broad search that returns 500,000 entries, it might actually crash your browser. So paging, and we will see later how we can use it, is a very, very important directive to use. If you want all of them, you set paging to -1. The default is the first 64 entries. So that has been very, very abstract so far. And can we use a type of metals as an entry? I think we are working on this for now. We are working on this still. I think alkali metals is so far not implemented yet. You would have to actually use this scheme here and explicitly use all the elements. So that's where the search function on the website is a little bit better still. I think Frisco is still working, Frisco Rose, who wrote the paper on this, who designed this, is working on making these things work still. Any other questions? Looking at the chat. Could you explain an example of mute and not here? I will get to that in just a second. One of the exercises contains this, and I can show you when we go to the Colab notebook. It's a good question. We will do plenty of exercises now because this has been very abstract and it's better to see it in action. Okay. If there are no more questions, then let's go back to our Colab notebooks. Here are the operators again. Here we can see this is the help text that you can get with including the references. Here are a few examples, but we will go through the examples now. Here's the schema. Here we can see, for example, the volume of the cell, and in the schema we see a description and a couple of internal things, the number, the type of it. But the important thing is that we, here the syntax, for example, you can use this for the REST API. So the schema is very, very important, not just for Aflux, but here you can see all our keywords that we have available. Here's an example of how to use the loose operator, and you can use it. You can do it using the browser. For example, we want all all materials with a band gap between 0.5 and 0.7, which is 0.6 EV plus minus 0.1. Might take a little bit because we're searching through 3 million entries. But here you see we have a response in JSON format. Let's see, here's one. You can see this is a calcium, copper, iron oxide selenite compound, and we have a band gap of 0.5118. You always get the AUID and the AURL in case you want to look at the entry page, but this is essentially what you're getting back as JSON if you put this into your browser. Just to demonstrate that it actually works in the browser, we can just copy the link. All the Zoom commands are kind of in front of me. Yeah, it's loading. It might take a little bit. Here it is. So we see we have 878 results, but the result that is returned is only 20 because of the paging directive. Here we see paging is -1, which means return all entries, and then the 20 afterwards means display only the first 20. If we displayed all the 900 entries, that might actually get us into trouble in the browser. But to go through the command a little more closer, what this did here is it looked for the thermal conductivity that was calculated with a band gap of at least 6 electron volts. This is what the loose operator does, 6 electron volts or more. We can also use this in Python. I'll go through this slowly. So we need, first of all, a link to the app, which is on aflow.org/appy/aflux. Version 1.0 is the version you can use, or you can just leave that out. It would then go to the next deployed version. Here is the command that I was talking about earlier. The species are sodium and potassium. N species is 2. The E gap is between 2 and 5 electron volts, and we want to get the energy per cell. We want to get the first 64 entries. It's also yeah, we have paging 0, and that means that we get the first entries. It's actually not only going to be, oh, it looks like I actually misspoke. 0 returns all entries. I'm sorry. -1 is sorting in descending order. My apologies. 0 returns all entries, not making -1. But yeah, the directives are paging 0. And then we essentially just put that link together. I can actually also just print, just to make it clearer, server plus appy plus match book plus directives. This is the URL we will after all, or summons, that we will after all just put into the browser, and then Python will just open the URL and decode it into JSON, and then we can output it. You will see the results that we're getting. So the results of that link is here, and I'm going to show now, there was the question of how the mute operator works. We see, it's kind of hard to make this a little bigger, but if you add the mute operator to N species, for example, we see that N species is gone. It's not there anymore. So this is how the mute operator works. How can you print the whole list of implemented features? This is in the schema. So when we have, I think I showed this earlier. Where is it? Yeah, here, the schema. You can read through it and look at what the appropriate keyword is. I would actually recommend in that case to just go to the search page and look for your keyword. That might be easier than reading through a JSON file. But these are ways you can do this. A third way to do it is actually go to aflow.org. And there is something called the REST API docs that also has a list of keywords. So there's 3 ways you can go about this, whatever you prefer. But the schema is the canonical list of properties that we have. You're welcome. So there was a not operator that was also asked for. Thank you, Cormac. There's also the REST API paper, which has some of the properties, but we keep adding properties occasionally. So the schema is the most updated one. a not operator, let's see, what can we do? We can, for example, return the entries that have sodium and potassium that are binaries but not chloride. And let me actually make sure that we're printing the compound, for example. This can be a very large output now, so it might take a little bit. Oh, there it is. So not that much. We see there's like sodium iodide, there's potassium, there's some potassium, I think there might be an azide, potassium sulfide, but you will not find chloride in there. So just adding the exclamation mark in front of the chloride is one way to go about this. Who asked that? Mohammed, did that answer your questions? So it's excellent. So it's Aflux is essentially all about building that matchbook. This is, I think, this is the most difficult thing to do. The rest is just loading a URL and kind of packing it into JSON. And for that, we have a few exercises. So let me go through one of them, and then I'll let you play with the others. So we're using Aflux to retrieve the space group numbers of all materials that contain copper and titanium, but not vanadium. And the keyword that you need is space group relax, which you can find, for example, in the schema. So let's go through this slowly. I already gave you the server and the API to just build the link. So the first thing we need to define is the matchbook. What do we want? We want to limit the species to copper and titanium, but not vanadium. So the species has to contain copper, titanium, and not vanadium. So that's what the not operator is for. And we want the space group number, and the keyword is space group. That's the matchbook. So this is what is querying all the responses. The directive, since we want all of them, would have to be paging 0. Paging 0 returns everything. And we can combine this into a summons that is just matchbook plus comma plus directive. So the final URL will just be server plus API plus the summons. And I will just print the URL for now, just so you can see how this looks like in the end. This is essentially the entire query that you're going to get. And then we can just copy and paste this response command. This is the same for everything. It's really just grabbing a URL and opening a JSON. We're opening it as JSON. And then we just go through all the entries and print it. So what should we display? We want the space group. Let's say we want to print the AUID. We want to print the compound. And the space group relax. And that should do it. Here is the URL that it's using. And here we are. So we see we have a bunch of binaries, copper, 8, titanium 16, space group 227 is one example. And see, it's a lot of entries, a lot of binaries, and some ternaries. We get ternaries because we didn't specify that we wanted to have only copper and titanium. If you want to specify that it's only copper and titanium, you need to set n species to 2. Let me see. See if people so far can follow. Yes, yes, mostly. Okay. Yeah, this was, as I said, following along is not easy with something like that. So why don't you all jump into the exercises, into the other exercises, and ask any questions that you have for the next. Okay. I'm gonna go ahead and wrap up fairly soon. Just want to get through one more exercise so we can move this over to David. The other exercise, the exercises all work essentially the same way. You can take, for example, I'm just going to copy and paste it to make it a little bit quicker, especially this part here, because this is essentially all the same except for that your matchbook and maybe your directive is different. So what we want here is all the material. Oh yeah, sure, why not? That's not the exercise I wanted to do, but we can do that. Everything in the catalog, in the ICSD catalog that contains the element tin but not lead and that have a band gap between 1 and 3 electron volts. So the band gap between 1 and 3 electron volts, we use the loose operator here, and tin but not lead using the not operator, and paging 0. We can also just limit the catalog to catalog ICSD, and then we get the same thing. Counting the materials is really just printing the length of your response. And that should be it. Here's the link to that. Where's the 0? That's a good string. There's typo in there somewhere. Let's see without the catalog maybe. That gives us a response 404 without the catalog. Not sure why the catalog wasn't working. I'll have to look into that, but this is essentially one way to go about this, and this is a way how you can get the all the materials that have tin but not lead with a band gap between 1 and 3 electron volts. And with that, thank you for your attention. If you have any questions, feel free to keep sending me messages or send it into the chat. Oh yeah, sorry, what's paging 0? Paging 0 means retrieve all entries. You want to use the paging command, especially when you're in a browser, so you don't crash your browser if you get too many results. Paging 1 returns the first 64 entries to the entries 65 through 128. And with that, oh, thank you very much. Yeah, feel free to play a little bit more, do the other exercises, and play a lot with Aflux. It takes a lot of practice to get mastery of it, but it's a very nice tool. With that, I will stop sharing my screen and hand over to David.